Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine a world where the fastest computers on Earth aren't manufactured in sterile, multi-billion-dollar factories, but are grown in the depths of our oceans. For decades, the backbone of our digital existence has been silicon. From the smartphone in your pocket to the massive servers powering the internet, silicon semiconductors have reigned supreme. However, we are rapidly approaching what physicists call the silicon wall. As we shrink transistors to the size of a few atoms, the electrons themselves start to behave unpredictably due to quantum tunneling. To move forward, we don't just need better engineering, we need a completely different medium. Enter the diatom. Diatoms are a type of phytoplankton, microscopic single-celled algae found in nearly every body of water on the planet. They are famous among biologists for their frustules, exquisitely intricate cell walls made of hydrated silicon dioxide, or silica. These are essentially microscopic glass houses. While they might look like tiny pieces of jewelry or delicate lace under a microscope, these structures are actually one of nature's most advanced pieces of optical engineering. What makes these shells so special for the future of computing is their relationship with light. Diatoms have evolved over millions of years to manipulate sunlight with extreme precision, primarily to maximize photosynthesis while protecting themselves from harmful radiation. Their shells are filled with nanoscopic pores arranged in perfect geometric patterns. These patterns function as photonic crystals. In the same way that a semiconductor controls the flow of electrons, a photonic crystal controls the flow of photons, or light particles. Specifically, researchers have discovered that certain species of diatoms are uniquely tuned to interact with ultraviolet, or UV, light. This is the holy grail for the next generation of computing. Currently, the most advanced computer chips are made using extreme ultraviolet lithography. The smaller the wavelength of light used to print a chip, the smaller and more dense the transistors can be. But what if we didn't just use UV light to make the chips? What if the chips themselves ran on UV light? Ultraviolet computing promises speeds and data densities far beyond what is possible with visible light or electricity. Because UV light has a much shorter wavelength than visible light, it can carry significantly more information and be channeled through much smaller pathways. The problem has always been finding a material that can reliably guide and switch UV light at a nanoscopic scale without absorbing it or breaking down. Silicon, while great for electricity, is inefficient for UV photonics. Diatom silica, however, is naturally transparent to UV and its intricate core structures can act as a natural waveguide. Scientists are now looking into biotemplating. Instead of trying to build these complex UV conductive structures from scratch using expensive lasers, we can essentially farm them. By providing diatoms with specific chemical nutrients and controlling their environment, we can encourage them to grow shells that fit our technological needs. This is the birth of the phytoplankton semiconductor. The implications are staggering. Growing our hardware could drastically reduce the carbon footprint of the tech industry. Traditional semiconductor manufacturing is one of the most energy-intensive and chemically hazardous processes on Earth. It requires massive amounts of ultra-pure water and rare earth metals. Diatoms, on the other hand, require little more than sunlight, carbon dioxide, and silica. We are looking at a future where high-performance computing components are carbon-negative and biodegradable. Furthermore, the structural diversity of the over 100,000 species of diatoms provides a massive library of pre-existing designs. Some diatoms possess hexagonal lattices perfect for signal splitting, while others have spiral structures that could be used for encoding data in the orbital angular momentum of light. We are essentially walking into a biological warehouse of patented nanotech that nature has been refining for over 200 million years. We are still in the early stages of this revolution. Translating a biological shell into a functional logic gate requires bridging the gap between organic biology and rigid computer architecture. Researchers are currently experimenting with coating these silica shells in thin layers of conductive materials or using them as molds for synthetic polymers. But the path is clear. The future of computing isn't just digital, it's biological. As we push toward the limits of physics, nature reminds us that it solved the problems of miniaturization and efficiency eons ago. The next time you look at the ocean, remember that the key to the next supercomputer might be floating in a single drop of water. For more incredible facts like this, don't forget to subscribe and turn on notifications.